Well, I'm a little bit nervous. I'm a little bit nervous.
Why?
I'm already streaming, so please don't use bad words.
You can use bad words.
I can actually, but I should not. I'm about to read Designing That Intensive Applications book.
Are you already streaming?
Yes, I am.
I'm going to give you a super chat.
That would be really nice of you. I don't think you can actually.
What?
Like, I need 1,000 subscribers or something.
That's bad.
Yeah, it kinda sucks. Hmm, where is chapter 1? Okay.
Oh wait, I can hear you talking. Oh shit, I was about to fart.
Really funny.
Huh?
Really funny. Hey guys, this is Elias. Just a quick plug. This is the last video in this channel. Well, not probably the last video in this channel, but it's the first video I'm talking in English because I was about to stream in a new channel I just created. That is going to be my new main channel where I will be talking in English. But I cannot stream until 24 hours later because I just requested like the stream access. So I will stream this channel just because I want to. Um, yeah. So I will be reading this book. Like like it's a printed version. So I will not be reading all the book out loud because that will infringe copyright. But I will read some parts of the book and then say my thoughts or probably like Google some stuff. Um, show some examples. So yeah, as I said, the book is Designing That Intensive Applications by Martin Kaplan. Kapman. I think it's a pretty simple book for software engineering preparation. So yeah, let's keep starting. I'm currently on chapter 1. To be honest, I already read a little bit of this, maybe until chapter 2, but it was like a month ago or maybe even 2 months ago. So it's going to be like the first time for both of us, for all of us. Okay, reliable, scalable, and maintainable applications. The internet was done so well that most people think of it as a natural resource, like the Pacific Ocean, rather than something that was man-made. When was the last time a technology with a scale like that was so error-free? That's the phrase with which with this chapter starts. So many applications today are data intensive as opposed to compute intensive. For example, a dashboard, right? It's mostly showing data, maybe doing some kind of calculations like a total or average, but it's mainly data intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of data, and the speed at which it is changing. Okay, so a data-intensive application is typically built from standard building blocks that provide commonly needed functionality. For example, many applications need to store data so that key or another application can find it again later. Yeah, like a database. Remember the result of an expensive operations, a cache, allow users to search data by keywords or filter in various ways. Well, the most obvious example will be a search index. So, yeah, send a message to another process to be handled synchronously, like stream processing. Maybe, I don't know, RabbitMQ. Periodically, periodically crunch a large amount of accumulated data. So that will be batch processing, right? If that sounds painfully obvious, that's just because these data systems are such successful abstractions that we use them all the time without thinking too much. When building an application, most engineers wouldn't dream of writing a new data storage engine from scratch because databases are perfectly a good tool for the job. Well, basically mm, we are just pointing out what are the pillars of more applications. Yep. So let's keep going. But reality is not that simple. There are many database systems with different characteristics, SQL, NoSQL, or, time-based databases, even nowadays, or vectorial databases. Anyways, because different applications have different requirements. There are various approaches to caching, several ways of building search indexes, and so on. When building applications, we still need to figure out which tools and which approaches are the most appropriate for the task at hand. And it can be hard to combine tools when you need to do something that a single tool cannot do alone. This book is a journey through both the principles and the practicalities of a data system, of data systems, and how can you use them to build data-intensive applications. We will explore what different tools have in common, what distinguishes them, and how they achieve their characteristics. In this chapter, we will start by exploring the fundamentals of what are we trying to achieve: reliable, scalable, and maintainable data systems. We will clarify that those things mean, outline some ways of thinking about them, and go over the basics that we will need for later chapters. In the following chapters, we will be continue layer by layer looking at different design decisions that need to be considered when working on a data-intensive application. So while this chapter will be about the tools, I don't think it will be like maybe it doesn't talk about the specific technologies, but like how to connect them. Anyways, thinking about data systems, we typically think of databases, queries, caches as very different categories of tools. Mm, yeah, for example, when application is just starting, you probably will not need a kiwi, or well, it depends what kind of application you are doing, right? But most of standard applications will need even from the start a database and even a cache. So, okay. A Toke database and a message kiwi have some superficial similarity, but store data from some time. They have very different access patterns, which means different performance characteristics and thus very different implementations. So why would we lump them all together under an umbrella term like data systems? Many new tools for data storage and processing have emerged in recent years. They are optimized for a variety of different use cases, and they no longer nearly fit into traditional categories. For example, there are data stores that are also used as message queues, Redis. Well, Redis didn't start as a message queue, though, but yeah. And there are message queues with databases like durability warranties, like Apache Kafka, and the boundaries between these categories are becoming blurred. That's usually because a program like Redis Redis started for mostly catching stuff, right? But as it was used in a lot of programs, and for example, I'm building an application and I already have Redis, like I'm already using Redis, right? So I may need a kiwi, but having an instance of RabbitMQ could be expensive or not worth the hassle for the feature I need. So if Redis, even if it doesn't have the best kiwi system, like it has one, I will probably use code with that, just for the simplicity. And that's how usually big programs like keep getting features and more features and more features. Well, let's keep going. Secondly, Secondly, increasing many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. For example, if you have an application managed caching layer using memcached or similar for a full text search server, such as Elasticsearch, separate from your main database, it's normally the application codes responsibly to keep those caches and indexes in sync with the main database. Well, let's keep going. We'll have a picture that tries to explain, but I will try to explain what the picture is showing. It's basically a user that calls an API, so our API is our backend that has our custom application code. The custom application code reads a request and tries to check if it's already in the cache memory. If so, you send that, right? If there is nothing in the cache, then we will go to the primary database and execute some other code. And well, in this case, it's a full text index. It's like a search request. So API, application code, primary database, again some custom code, and then we will use a full text index such as Elasticsearch. And if there is an asynchronous task, we will use a message kiwi, which again connects to our custom code, right? So okay, let's keep reading. When you combine several tools in order to provide a service, the service interface of application programming interface, API, usually hide those implementation details from the clients. Now you have essentially created a new special purpose data system from smaller general purpose components. Yeah, that's an interesting way to say it. Your composite data system might provide certain guarantees that the cache will be correctly invalidated or updated on writes so that outside clients see consistent results. You are now not only an application developer, but also a data systems engineer. Hey, that's cool. I'm a data systems engineer though. If you're designing a data system or a service, a lot of tricky questions arise. How do you ensure that the data remain correct and complete, even when things go wrong internally? How do you provide consistently good performance to clients, even when parts of your system are degraded? How do you scale to handle an increasing load? What does a good API for the service looks like? There are many factors that may influence the design of a data system, including the skills and experience of people involved, legacy system dependencies, the time scale for delivery, your organization's tolerance, or different kinds of risk, regulatory constraints, etc. Those factors depend very much on the situation. In this book, we focus on three concerns that are important in most software systems: reliability, scalability, and maintainability. Reliab- Reliability. The system should continue to work correctly, performing the current functions at a desired level of performance, even in the face of adversity. Adversity such as hardware or software faults, or even human errors. Scalability. As the system grows in data volume, traffic volume, or complexity, there should be a reasonable way of dealing with that growth. Maintainability. Over time, many different people will work on the system, engineering and operations, both modeling current behavior and adapting the system to new use cases. And they should all be able to work on it productively. Yeah, these words are often cast around without a clear understanding of what they mean. In the interest of a thoughtful engineering, we will spend the rest of this chapter exploring ways of thinking about reliability, scalability, and maintainability. Then in the following chapters, we will look at various techniques, architectures, and algorithms that are used in order to achieve these goals. Those goals. Hmm, yeah, like if you have the opportunity to build a data system from scratch, obviously you will have like these three principles in your mind, right? Hmm, but when you get to like a legacy project or not even legacy, like a project that is being worked on, you usually don't see this stuff. Less in my work experience. Anyways, let's start with reliability. Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectations include the application performs a function that the user expected, so basically the application works. It can tolerate the user making mistakes or using the software in unexpected ways, so it handles errors. It performs good enough for the required use case under the expected load and data volume. And also, the system prevents any unauthorized access and abuse. If all those things together working, if all those things together mean working correctly, then we can understand reliability simply as continuing to work correctly even when things go wrong. Yep, the things that can go wrong are called faults, and systems that anticipate faults can cope with them are called fault tolerant or resilient. The former term is slightly misleading. It suggests that we could make a system tolerant of every possible kind of fault, which in reality is not feasible. If the entire planet Earth and all servers on it were swallowed by a black hole, oh, sorry. If the entire planet Earth and all servers on it were swallowed by a black hole, tolerance of that fault would require web hosting in probably a lot in space. Yeah, good luck getting the budget for that item approved. So it only makes sense to talk about tolerating certain types of fault. Yeah. Mm, this made me think about, you know, I was talking with the AWS certified architect some like probably 2 months ago. No, maybe even more, like 3 or 4 months ago, when there was like an AWS outage. So like even if your AWS architecture is pretty much perfect or like is fault tolerant and has like all the correct items, like if the whole AWS goes down, like your system is down too, right? So yeah, I don't know, use an idea. Note that fault is not the same as failure. A fault is usually defined as one component of the system deviating from its specs, where a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of a fault to zero. Therefore, it's usually best to design a fault tolerance mechanism that prevents faults from causing failures. In this book, we cover several techniques for building reliable systems from unreliable parts. Counterintuitively, that's a big word. I'm not a native English speaker, so well, you already probably guessed that. Anyways, in such fault-tolerant systems, it can make sense to increase the rate of a fault by triggering them deliberative. For example, by randomly killing individual processes without warning. Many critical bugs are actually due to poor error handling. By deliberately including inducing faults, we ensure that the fault tolerance machinery is continually exercised and tested, which can increase your confidence that faults will be handled correctly when they occur naturally. The Netflix Chaos Monkey is an example of this approach. I just remember like when Cloudflare had an outage too, and it was because they were using unwrap directly. If you ever code it in Rust, like you can unwrap a value that is, you got like a maybe type which receives a type T. So like if you unwrap, you get directly T, right? But you are not handling the error. You are just saying, hey, trust me, like the value is correct. So yeah, just an example of how you can be overconfident. I guess they were probably thinking like, okay, this is my own code. I know the exceptions. Like it's always going to be correct, so we don't need to handle this case. And they just unwrap like the value correctly directly. But yeah, mm, I don't know. Let's keep going. Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure because no cure exists. This is a case with security matters. For example, if an attacker has compromised a system and gaining access to sensitive data, that event cannot be undone. However, this book mostly deals with the kinds of faults that can be cured, as described in the following sections. Well, we have hardware faults. I'm actually pretty interested in this because I most of my experience has been working directly with, first of all, cloud services where you don't even have access to the real machine. And when I don't have access to the real machine, like it's usually used like, using SSH or something. So to be honest, I don't have that much of hardware experience. Let's see what it says. When we think of cases of system failure, hardware faults quickly come to mind. Hard disk crash, RAM becomes faulty. Well, I have dealt with a lot of issues with RAM, for example, with Java or C Sharp services. Anyways, the power grid has a blackout, someone unplugs a RON network cable. Hey, that sucks. Anyone who ha- who has worked with large data centers can tell you that these things happen all of the time when you have a lot of machines. Hard disks are reported as having a mean time to failure of about 10 to 50 years. Thus, on an storage cluster with 10,000 disks, we should expect on average one disk to die per day. That's a lot. Our first response is usually to add redundancy to the individual hardware component in order to reduce the failure rate of the system. This might set up in a RAID configuration. Server may have a dual power supplies and hot swappable CPUs, and data centers may have batteries and diesel generators for backup power. When one component dies, the redundant components can take its place while the broken component is replaced. That's like horizontal scaling for hardware. Probably it comes from hardware stuff, actually. Yeah. This is okay. Let's keep going. This approach cannot completely prevent hardware problems from causing failures, but it is well understood and can often keep a machine running uninterrupted for years. Until recently, redundancy of hardware components was sufficient for most applications, since it makes a total failure of a single machine rare. Fairly rare. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic in most applications. Thus, multi-machine redundancy was only required by a small number of applications for which high availability was absolutely essential. However, as data volumes and applications computer demands have increased, more applications have begun using larger numbers of machines, which proportionally increase the rate of hardware faults. Moreover, in some cloud platforms, such as Amazon Web Service (AWS), it's fairly common for virtual machine instances to become unavailable without a warning, as the platform are designed to prioritize flexibility and elasticity over single machine reliability. Hence, there is a move towards systems that can tolerate the loss of entire machines by using software fault tolerance techniques in preference or in addition to hardware redundancy. Such systems also have operational advantages. A single server system that requires planned downtime if you need to reboot the machine, to apply a system security patch, for example, or like updating devs or something like that. Whereas a system that can tolerate machine's failure can be patched one node at a time without downtime of the entire system. That's called a rolling upgrade. Okay, we already saw hardware faults. Well, use hardware faults. Now read about software errors. We usually think of hardware faults as being random and independent from each other. One machine disk failing does not imply another machine disk is going to fail. There may be a weak correlation, for example, the document cause, such as the temperature in the server rack. Yeah, that's really specific. But otherwise, it is unlikely that a large number of hardware components will fail at the same time. And that's actually different for software errors, right? Like, I'm pretty much sure like, you have the same software in all the machines. So if there is a software error, like, all your machines are fucked, basically. Well, let's keep reading. Another class of fault is a systematic error within the system. Such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than uncorrelated hardware faults. Well, of course, a software bug that causes every instance of the application server crash when given a particular bad input. For example, consider the leap second on June 30 of 2012 that caused many applications to hang simultaneously due to a bug in the Linux kernel. I was 6 years old. Not really, not even 6 years old. I was 5 years old at the time. If I remember correctly, I had my first computer when I was around five. You know, I remember installing like a trucked version of Minecraft when I was like 6 or 7, probably. Good times. Anyway, I run a web process that uses up some shared resource, CPU time, memory disk, space, or network bandwidth. Let's check if there is some wonder. Thanks, bro. This will break my speaking. Hey, José, ¿estás ahí? ¿Cuántos años? ¿No? Anyways, software errors. What's next? Okay, a service that the system depends on that slows down, becomes unresponsible, or starts returning a corrupt response. Cascading failures where a small fault in one component triggers a fault in another component, which in turn triggers further faults. The bugs that cause this kind of server faults often lie dormant for a long time until they are triggered by an unusual set of circumstances. Yeah, so like these are bugs that, for example, if there is a QA team, like the QA team didn't catch, so they end up in production until they get like a bad input from a user or a malicious attacker. And the user, the system trash. I'm getting distracted. Yeah, like I should probably. Yeah, okay. There is no quick solution to the problem of systematic faults in software. Well, it's usually patching the bug, right? Like debugging, see what went wrong. If it's for a specific input, like you usually have logs, like right? Like I don't know, in a try catch, you usually log the error or have some kind of traceability system. But let's see what it says. A lot of small things can help. Carefully thinking about assumptions, yes, and interactions in the system, through testing, process isolation, allowing processes to trash and restart, measuring, monitoring, and analyze system behaviors in production. If a system is suspected to provide some guarantee, for example, in a message queue, that the number of incoming messages equal the number of outgoing messages, it can constantly check itself while it's running and raise an alert if a discrepancy is found. That's a good idea. Like, I don't know, I build a system in a way that I know a condition will always be true. So then I can have like, I don't know, on a strip, or maybe it's even integrated into the system itself that checks, is this condition still true? If not, something is going wrong, probably, right? This is a really good example. I will repeat it once again. For example, in the message queue, the number of incoming messages equals the number of outgoing messages. Well, that's a well example. You can check if that's true, then the application is going fine. Unless it's, well, if that's true, you cannot say that the application is going fine. But if that's not true, you can say the application is in fact not going fine. Well, let's see another kind of error. Human errors. Humans design and build software systems, and operators who keep the systems running are also humans. Usually. This is 2026. Maybe this text is a little bit outdated. Not really. Even when they have the best intentions, humans are known to be unreliable. For example, one study of a large internet service found that configuration errors by operators were the leading cause of outage, where hardware faults, server or networks, played a role in only 10 to 25 of outage. Well, I'm actually interested in the percentage because if hardware is like, I don't know, 20%, which is pretty much in the higher end of the range given here, then 80% of all the errors are, configuration errors. That's quite high. Well, configuration errors, hardware errors, or software errors. I don't know. The memory, like the program is maybe using a way too much RAM or something. Anyways, let's keep going. How do we make our systems reliable in spite of unreliable humans? The best systems combine several approaches. Design systems in a way that minimizes opportunity for error. For example, well-designed abstractions, APIs, and admin interfaces make it easy to do the right thing. Well, and admin interfaces that make easy to do the right thing and discourage the wrong thing. However, if the interfaces are too restrictive, people will work around them, negating their benefit. So this is a tricky balance to get right. Yeah, for example, in my current work, like my software engineer, I'm currently working with some. I should not say that actually. Yeah, but anyways, like there is an interface to create, let's say, a kind of object, but it's like a pretty long formulary, and you need to fill up a lot of stuff. So I usually just end up doing some queries in the database. It's just because it's too much work to do it using like the admin panel. Of course, for like a normal user, it's okay, right? Like they will use their mouse and just type some stuff. But usually technical people, which are the ones that will be configuring systems, right? They like a little bit more freedom. Usually. I also know developers that really like, like, hey, click here to deploy or like zero configuration stuff. But yeah, I will say most of the developers like freedom. Anyways, tests are all at all levels, from unit tests to whole system integration test and manual test. Automated, automated testing is widely used, well understood, and especially valuable for covering corner cases that rarely arise in normal operation. Well, of course. Nowadays, when I write some code, like I always ask Cloud, try to make some tests that break this code in some edge cases. Like, I don't know, I write a very simple function and then I ask Cloud the code or, any other AI agent, like to find some edge cases for the function. This depends. I mean, I was going to give an example, like let's say you take a number and all your operations assume that the number is positive, right? Like major than zero. And Cloud Code sometimes gives you like pretty bad input, like I don't know, negative 69 or something pretty weird. Like it's good if your function, mm, like you end up trying to solve some cases that they do not usually arise, but that's exactly what the book is covering. Like even you should not trust your system. You should code defensively, even if you are quite sure that your function will always get, like positive numbers. It does not do that much of harm to have like an if your number is minor than zero, then throw a range error or whatever your programming languages give you, right? For example, I'm pretty sure in JavaScript we have the class range error, and most languages have something like that, or you can create custom errors. So yeah, yes, yes. Let's keep going. Set up detailed and clear monitoring, such as performance metric and error rates. In other engineering disciplines, this is referred to as telemetry. Once a rocket has left the ground, telemetry is essential for tracking what is happening and for understanding failures. Monitoring can show us early warning signals and allows to check whether any assumption or constraints are being violated. When a problem occurs, metric can be invaluable in designing the issue. Well, of course, you should have a logging system with different kind of logging levels that should be configurable, I don't know, in the environment variables or stuff like that, right? So yeah, implement good management practice and training. A complex and important aspect and beyond. Well, implement good management practice and training. This is a complex and important aspect and beyond the scope of this book. Well, of course, that's a discipline by itself. How important is reliability? Reliability is not used for nuclear power stations and air traffic control software. More mundane applications are also expected to work reliable. reliable. Bugs in business applications cause loss in productivity and legal risk if figures are reported incorrectly. An outage of e-commerce sites can have huge costs in terms of lost revenue and damage to reputation. Even in non-critical applications, we have a responsibility to our users. Consider a parent who stores all their pictures and video of their children in your code application. How would they feel if the database was suddenly corrupted? Will they know how to restore it from a backup? Well, they probably don't. There are situations in which we may choose to sacrifice reliability in order to reduce development costs. Example, when developing a prototype product for an unproven market. Like a minimal viable product, an MVP. Yeah, usually for an MVP, you're not looking for reliability, you are just looking to showcase application and like, hey, I found this problem and I built like a minimal application to solve it, blah blah blah. And then you raise some money or win some hackathons. Okay, there are situations in which we may choose to sacrifice reliability in order to reduce development. I already read that. Okay, but he says, but we should be very conscious of when we are cutting corners. Yeah, so even if you are not making your application reliable, you should be conscious of that, right? Like, hey, this is an MVP. I will not put real user data here. Or if I put some real user data here, like I have like a to-do list or I don't know, some ticket or something. Anyways, let's talk about scalability. We already talked about reliability. Well, and we need to talk about availability, no, scalability and maintainability. Scalability. Even if a system is working reliable today, that doesn't mean it will necessarily work reliable in the future. One common reason for degradation is intrusive load. Perhaps the system has grown from 10,000 concurrents to 100,000 concurrent users, or from 1 million to 10 million. Perhaps it's processing much larger volumes of data than it did before. Scalability is a term we use to describe a system's ability to cope with intrusive load. Note, however, that this is not a one-dimensional label that we can attach to a system. It's meaningless to say X is scalable or Y doesn't scale. Rather, discussing scalability means considering questions like if the system draws in a particular way, what are options for coping with the draw, and how can we add computing resources to handle additional load? Well, there are different techniques. We probably will be, I don't know, the most basic one is usually like horizontal. Well, the most basic one is actually vertical scaling, right? Like just making your machine bigger. The second one will be usually be horizontal scaling, which it's going to depend on what framework or what runtime, what programming language you are using, right? For example, for a Node.js application, it's actually like it's pretty much a most usual way to deploy an application is like in a horizontal setup, right? You have a couple of Node.js instance, or maybe in the edge, you have like some functions in the edge, so they are automatically turn on, turn off, and you can have thousands of functions at the same time when your traffic is higher. And yeah, let's keep going. Describing load. First, we need to so succinctly, well, you need to concisely describe the current load on the system. I will mark this word because I do not actually know how to read this out loud. I mean, I don't know what it means. It's pretty much writing the same in Spanish. Yeah. Only then can we discuss load questions. What happens if our load doubles? Load can be described with a few numbers which we call load parameters. The best choice of parameters depends on the architecture of your system. It may be requests per seconds to a web server, the ratio of reads to writes in a database. If your application is write heavy or read heavy, maybe. Like you can choose a DB based on that, or many other configurations. So also the number of simultaneously active users in a chat room, the hit rate of a cache, or something else. Perhaps the average case is what matters for you. Or perhaps your bottleneck is dominated by a small number of extreme cases. To make this idea more concrete, let's consider Twitter as an example, using data published from 2012. Two of Twitter's main operations are post a tweet and stroll, your home timeline. So post a tweet, a user can publish a new message to their followers. Well, I wasn't around in 2012, but most of my Twitter feed is not from people I actually follow. Okay, let's just keep reading. But okay, at 2012, there were around 5K requests, so 5K posts tweeted per second. And in a peak, there were 12,000 requests per second. That's a lot. In the home timeline, a user can view tweets posted by the people they follow, which had 300 requests per second, 300,000 requests per second. So while there was a lot of tweets being posted per second, this application is clearly more read heavy than write heavy. Like is 60 times, there are 60 times more requests to see the timeline. And actually the timeline got a lot of data because when you post a tweet, like you are posting the data, you are not getting data from the server more than, a success code or an error code or something, right? But to consume your home timeline, you actually need to pull a lot of data from the server. So yeah, it's a read intensive application. Simply handling 12,000 writes per second, the peak rate for posting tweets, will be fairly easy. Well, I don't know if fairly easy. Like, I forget it. Some social media application that's even quite a lot for today's standards. But yeah, let's say it is. However, Twitter's scaling or X scaling challenge is not primarily due to tweet volume, but due to fan out. Each user follows many people, and each user is followed by many people. So it's a many-to-many, you know, database relationship. There are broadly two ways of implementing these two operations. Posting a tweet simply inserts a new tweet into a global collection of tweets. Yeah, that's like your your MVP implementation. I don't think they are doing that, or that's it. When a user requests their home timeline, look up all the people they follow, find all the tweets of for each of those users, and merge them sorted by time. In a relational database, you could write a query such as, and there is a query. Or the query is quite simple, right? Like select all tweets from users, well, select the tweets and users from tweets, and you make a join with the users and the follow table. So yeah, maintain a cache for each user's home timeline, like a mailbox of tweets for each recipient user. When a user posts a tweet, look up all the people who follow that user and insert a new tweet into each of their home timeline caches. The request to read the home timeline is then cheap because the result has been computed ahead of time. Yeah, but the first time will be quite expensive. Mm, yeah, have some pictures here. Yeah, so user posts a tweet, then let's say I post a tweet, then my followers will need to query that tweet, right? So yeah, the first version of Twitter is at approach one. That's what I say. That's like your I don't know your MVP approach. Like if you are just thinking naively about it, it's like the easiest way to do it. But then the system struggled to keep up with the load of the home timelines queries. Yeah, this query is not exactly expensive, but it's neither cheap. So that makes sense. So the company switched to approach two. This works better because the average rate of published tweets is almost 2 orders of magnitude lower than rate of home timeline reads. And so in this case, it's preferable to do more work at the right time and less at read time. So, we have like 300,000 queries to get the tweets. And to make a request like that makes you join some tables and pull a lot of stuff. So it's better if we have like a timeline per user, and each time we post a tweet, we write to all their timelines. So when the user tries to get their timeline, it's already done, right? And as trying to get your timeline occurs a lot more often than posting a tweet by magnitude of order. Like, yeah, this is a pretty good approach. I like it. That's interesting. Well, the last part is actually also interesting to read. Let me show it to you. But this average hides the fact that the number of followers per user varies wildly, and some users have over 30 million followers. This means that a single tweet may result in over 30 million writes to the home timelines. Doing this in a timely manner, Twitter tries to deliver tweets to followers within 5 seconds. 5 seconds. It's a significant challenge. So yeah, let's say I have used like 2 followers on Twitter, and if I tweet something, like Twitter just needs to date 2 timelines. But what if I had like 30 millions, like in the example? Like one tweet of mine will need to do like 30 million queries to update all of those timelines. Let's see what Twitter did. In the example of Twitter, the distribution of followers per user may be weighted by how often those users tweet. Is a key load parameter for discussing scalability. Oh, that's quite cool. It's like your asymptotical function for the system, since it determines the fan out load. Your application may have very different characteristics, but you can apply similar principles to reason about its load. The final twist of Twitter anecdote, now that approach 2 is rosely implemented, Twitter is moving to a hybrid of both approaches. Most user tweets continue to be fanned out to home timelines at the time when they are posted, but a small number of users with a very large number of followers, celebrities, are accepted from this fan out. Tweets from any celebrity that the user may follow are fetched separately and merge out with that user's home timeline when it's read, like in approach 1. This hybrid approach is able to deliver constantly good performance. We will revisit the example in chapter 12 after we have covered some of the technical run. Well, that's actually quite cool. Hmm. So for most users that do not have that many followers, it's preferable to do the work. You can have it, like you can see this as a multiplication. For most users, they do not have that many followers, and the quantity of tweets per second is actually quite low. So a low number by a low number, I mean, these numbers are major than 1, so the number is bigger, right? But it's not that big. But in the model 1, there are like the number of queries per second is really big, right? So if we try to computate all of the tweets at that second, is like a big number multiplied by a normal number is even bigger than the other. But in those special edge cases where like an account has a massive following, it actually makes sense to do the first approach, right? Because the other operation is expensive. So yeah, an hybrid approach works pretty good here. I like this problem. Describing performance. Once you have described the load on your systems, you can investigate what happens when the load increases. You can look at it in 2 ways. When you increase the load parameter and keep the system resources, CPU, memory, network bandwidth, etc. unchanged, How is the performance of your system affected? And when you increase a load parameter, how much do you need to increase the resources if you want to keep performance unchanged? Those are two good questions. Both questions require performance numbers. So let's look briefly at describing the performance of a system. In a batch processing system such as Hadoop, we usually care about throughput, the number of records we can process per second, or the total time it takes to run a job on a dataset of a certain time. In online systems, what's usually more important is the service response time. That is, the time between a client sending a request and the client actually receiving a response, right? So latency and response time. Latency and response time are often used synonymously, but they are not the same. The response time is what the client sees, beside the actual time to process a request, the service time. It includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which it's latent awaiting service. So, mm, let's say we have like a synchronous server, like a Python server, or even I will say, well, I could not say a PHP server because the usual setup has like 4 instances of PHP or something. But yeah, like let's say we have a Python server from 5 years ago that is not using multi-threading or any weird stuff, and it handles one request per it handles one request and waits until handling all the requests to go to the next one. So latency will be, let's say I have the same backend and I have like two endpoints, one that processes data and one that that serves the front end. So let's say user A do some click and is processing data, so the server is busy, it cannot respond. So the user B is trying to get to the dashboard and it will not load until, well, the user A gets its report, right? So latency will be all the time until the request is accepted. So the previous process already ended. I mean, the previous job already ended. So the endpoint returned something. And the wait response time is, the time it had to wait and the time the server also take to send the HTML or whatever it's serving, right? Anyways, even if you only make the same request over and over again, you will get a slightly different response from time on every try. In practice, in a system handling a variety of requests, the response time can vary a lot. We therefore need to think of response time not as a single number, but a distribution of values that you can measure. Well, stats. That's quite cool. Hmm. Well, they're showing an image with like a bar chart with the time of each request, and it shows that most of if the median is here, most of the requests are actually just below the median, right? If most of the requests are below, there needs to be some cases where the requests really take a long time to put the median higher up, right? So here is given some example of why that can happen. Some of the example given were random additional latency could be introduced by a context switch to a background process, yeah, the loss of a network packet and TCP transmission. I will say this is more often than the previous one. A garbage collection pause, which is really hard to debug actually. A page fault forcing a read from a disk, or even a mechanical aberration in the server rack. It's common to see the average response time of a service reported, Strictly speaking, the term average doesn't refer to any particular formula, but in practice is usually understood as the arithmetic mean. Given any values, add up all the values and divide by n. However, the mean is not very good metric if you want to know your typical response time, because it doesn't tell how many users actually experience the delay. Usually it's better to use percentiles. If you take a list of response time and sort it from fastest to slowest, then the median is the halfway point. For example, if median response time is 200 milliseconds, then that means half of your requests return in less than 200 milliseconds, and half of your requests take longer than that. So most of the users, well, half of the user, at least half of the user got their response in just 200 milliseconds. This makes the median a good metric. If you want to know how long users typically have to wait, half of the user requests are served in less than the median response time, and the other half take longer than the median, right? The median is also known as the 50 percentile and sometimes abbreviated as P50. Note that the median refers to a single request. If the user might make several requests over the course of a session or because several resources are included in a single page, the probability that at least one of the system is lower than the median is much greater than 50%. In order to figure out how bad your odors are, you can look at higher percentiles. The 95 percentile, the 90 percentile, and 99.9 percentiles are common. For example, if the 95 percentile response time is 1.5 seconds, that means 95 out of 10 requests take less than 1.5 seconds, and 5 out of 100 requests take 1.5 seconds or more. High percentiles of response time, also known as tail latencies, are important because they directly affect user experience of the server. For example, Amazon describes response time requirements for internal service of the 99 percentile, even though it only affects 1 in 1,000 requests. This is because the customers with the lowest requests are often those who have the most data in their accounts because they have made many purchases. That is, they are the most valuable customers. Let's read that one. Sentence again. For example, Amazon describes response time requirements for internal services in terms of 99th percentile, even though it only affects 1,000 requests in 1,000 requests. This is because the customers with the slowest request are often those who have the most data in their accounts because they have made many purchases. That is, they are the most valuable customers. It's important to keep those customers happy by ensuring the website is fast for them. Amazon has also observed that a 100 millisecond increase in response time reduces sales by 1%. Well, frustration from users, right? And other reports that a 1 second slowdown reduces customer satisfaction metric by 16%. Hey, tricky. On the other hand, optimizing the 99.99 percentile, slowing 1 in 10,000 requests, was deemed too expensive and not yield enough to benefit for Amazon purposes. Reducing response time at very high percentiles is difficult because they are easily affected by random events outside control, and the benefits are diminishing. For example, percentiles are often used in a server level objective (SLOs) and service level agreements (SLAs). Contracts that define the expected performance and availability of a service. An SLA may state that a service is considered to be up if it has a median response time of less than 200 milliseconds and a 99 percentile under 1 second. Okay. If the response time is longer, it might as well be down. Hmm. Okay. And the service may be required to be up at less than 99.9 of the time. This metric sets the expectation for clients of their service and allow customers to demand a full or refund if the SLA is not met. Queuing delays often amount for a larger part of the response time at a high percentiles. As a server can only process a small number of things in parallel, limited for example by its number of CPU cores, it only takes a small number of slow requests to hold up the processing of subsequent requests, and in fact sometimes known as head of line blocking. That's what I was talking about before with, the sample Python server I mentioned. So yeah, even if those subsequent requests are fast to process on the server, the client will see a slow overall response time due to the time waiting for the prior request to complete. Yeah, that's what I was saying. Let's say our server has two endpoints, like the front end and something to process data. Our server has only one thread, well, only one core, or maybe it has many cores, but all of them are being used to process data at the same time. The next request that it comes will have to wait until at least one of those cores is free. When generating load artificially, in order to test scalability of the system, the load generating client needs to keep sending requests independently of the server response time. If the client waits for the previous request to complete before sending the next one, that behavior has the effect of artificially keeping the queue shorter in the test than they will be in reality, which skews the measurements. Well, guys, it's quite late for me. Well, it's not a surprise, but I read a lot slower if I'm having to read aloud, but it probably makes it better for my understanding. It makes it better for my understanding. Oh, I'm about to finish the chapter. Yeah, we probably can finish this tomorrow. Let me just read this part so we stay on the next one. And hopefully the next one will be in the huge channel that I mentioned it, and not in this one. So yeah. High percentiles become especially important in backend services that are called multiple times as part of serving a single end user request. Even if you make the calls in parallel, the end user request still needs to wait for the lowest of the parallel calls to complete. Yeah, that's like promise.all in JavaScript. So it just takes one slow call to make the entire end user request slow. Even if only a small percentage of backend calls are slow, the chance of getting a slow call increases if an end user request requires multiple backend calls. So a higher proportion of end user requests end up being slow, an effect known as tail latency amplification. If you want to add response time percentages to the monitoring dashboard for your services, you need to efficiently calculate them on an ongoing basis. For example, you may want to keep a rolling window of response time of requests in the last 10 minutes. Every minute, you calculate the median and various percentiles over the values in the chat in that window to add those metric on a graph. The naive implementation is to keep a list of response times for all requests within the time window and to sort that list every minute. If that's too inefficient for you, there are algorithms that can calculate a good approximation of percentiles at minimum CPU and memory cost, such as forward decay. I guess that's the most common one. Oh, and my mic is also about to die. I got 10%. That's not good. Well, we have other algorithms, and also beware that averaging percentiles to reduce the time resolution or to combine data from several machines is mathematically meaningless. The right way of aggregating response time data is to add the histogram. Okay, that was a pretty good lecture. We are this. We probably have, I don't know, like 20 or 30 streams to go. I'll put a small mark here. See you tomorrow, hopefully. Take care. No, my bicep is a little not good. Also to be better. Yeah.